So my plan in this video is it's not to go through using integration by parts. I've done other videos on that. This is like an add-on because I really wanted to spell out the reason for why we choose which one we define is going to be the U out of this bit. So if you don't know what I'm talking about, you need to watch the other videos first, really, before you get into this one. But this one I really wanted to get over the message, what the whole purpose is of integration by parts and how that helps us choose which term we use as the U term. And it's all about getting rid of one of these terms. We've got one of these values because we've got here an x times an x. So we've got a product basically and we can't integrate that. Integration is, whilst in differentiation you've got quite nice easy formulas for solving a lot of complicated issues, it's a bit more tricky when you get to integration. That's when we start introducing all the different tools like integration by parts, integration by substitution, long division, the other one that's name's gone out of my head, partial fractions. All these methods are ways to do it, or we just use software, frankly, to make it easier. But sometimes software might not quite get us there. We might have to do a bit of manipulation first, and this could be an example of manipulation first. The other reason we might do it is because we might want to get this into from this to this kind of layout, really. That might allow us to use another tool to solve it as well. But generally speaking, the point I'm making here is why do we decide that this one is going to be the U term, making this one the dv dx. And the thing to look for is it's the x value term that we're going to make into the U. If we had something like this, e to the x cosine x, then we're not going to be able to solve it by this method, because the thing with this is when we differentiate this, then the x disappears and we've stopped this being a product. We've made it into just one simple term. If you look over here, when we've expanded out the formula, and this is the general formula, this would become just, in this example, would become just 8. So we've no longer got a product here. So it's made it solvable. In this situation, or if we made this into U, it doesn't disappear, it stays there. So you've still got the problem. This doesn't disappear, it stays there. Okay, so them two terms, trig functions, Euler's number, logs, all these things, they don't disappear. The only way you can get them to disappear is when you differentiate a polynomial x. It will eventually disappear if you differentiate enough times. So that's why we choose it. So look for where the x term is and decide that that one's going to be a u. And then when we differentiate that, the du dx part, it actually just becomes 8. If this was squared, when we differentiate that, we'd get 16x. We'd still have an x. So we'd have that there. So we'd have to, this is where it gets long-winded, we would have to apply the integration by parts again to this part of the solution. And obviously if this was to a 3, it'd get really painful. So you'd actually be applying integration by parts in that situation 3 times in one solution. So then would get a bit tedious. But fortunately we have software to help us with these things. But that aside, that's what you're doing. You're aiming to get rid of the x term, the polynomial. And the only way you can get rid of it is by differentiating it. So eventually the x disappears. And that is the reason. That's the number one to be looking for in these situations. And I say if there's not a term like that, if it's something like this or log or something, then forget it. You're not going to do it this way anyway. You're going to have to find another solution.